There's Amanda. Amanda's ready. Okay. So we'll introduce Amanda Tveite here, who is a master's student in the Integrated Biosciences program at the University of Minnesota Duluth, conducting avian ecology research within the labs of Dr. Alexis Grindy and Matt Ederson. Building upon her background in math and extensive field experience as a bird bander, her current research focuses on applying quantitative problem-solving techniques to ecological topics. Amanda.
Hi, everybody. I'm Amanda Tveite. I'm a graduate student at the University of Minnesota Duluth with Drs. Alexis Grindy and Matt Ederson. And I'm going to be talking about how we can use life cycle modeling in conjunction with field data to inform conservation and management decisions. So for a brief outline, I'll be talking initially about a specific project that we've been working on in the Avian Ecology Lab at NRRI since 2019. Kara touched on it some, so I'm going to be expanding on that a little bit. So we'll start by talking about background about golden wing warblers, and then we'll talk about the study specifically, and then we'll move into the modeling and how we can combine the two. So first off, golden wing warblers are these beautiful little long-distance migrants that breed around the Great Lakes, and they winter largely in Central America. They're classified as a species of conservation concern in Minnesota, and they nest in shrubby wetlands and early successional forest. Those two habitats are really difficult to manage for, and so it is really important that we are studying this species and how we can help conserve them. Minnesota is the perfect place to be studying them because the global population is estimated about 400,000, and we think about 50% of that population breeds in Minnesota. So this is a lovely animation from eBird from 2006 to 2020, showing where golden wings are throughout the year. So we can see them all moving from their wintering grounds up to their breeding grounds, largely in Minnesota. Okay. So the study that I am using data from was focused on thinking about how these two different habitat types compare in terms of nest success and fledgling survival. So we had a few different phases each year of our data collection. So we were out in the field pretty much all breeding season for the golden wings. So we would start by during the pair building and nest building phases, we would be target netting females and putting transmitters on them so that once they were in nests, we could use telemetry to locate their nests. We also were using classic nest searching techniques to find nests, also during that same time and through incubation and through the nestling phase. So once we found nests, we were monitoring them throughout the nestling phase. And we would actually visit the nest twice during that time and take measurements of nestlings. And on our second visit, we would also attach radio transmitters to those nestlings, or to half the nestlings in each nest. We were also color banding all of the nestlings so that we could identify them all when we found them in the field. And so over 6 years, we found 125 nests, of which about 45 of the nests, which is about 36%, successfully fledged at least one young. And then we banded 189 individuals, attached 126 transmitters. So after the nestlings fledged, we would track them every day through telemetry. We would make note of their location, their behavior, and any other birds that we were finding them with. And then after the breeding season, or after we lost track of the fledglings, after they'd moved far enough from their natal grounds, we were also doing habitat surveys at every point where we found a fledgling, and at every nest point, and then at paired points. So we saw numerous threats to nests and fledglings. The main the main threat that we were seeing was a threat of predation. And so over the 6 years of field work for the project, 53 of the nests, or about 42%, failed due to predation. Anything and everything wants to eat nestlings and fledglings. We saw everything from squirrels and snakes to deer and bears, as you'll see in this video. And from the years 2022 to 2024, we also had cameras on the nests so that we could collect predation data. So this is a kind of unfortunate video of what a nest predation might look like. So we also saw nest failure due to weather. So golden wings are ground nesting warblers. Bad idea if you ask me, but it means that they are really vulnerable to weather events. So heavy rain and intense storms can lead to nest failure as well. And in the first couple of days after they fledge, fledglings are also pretty vulnerable. They stick close to the ground. They can't move very much. They're just trying to be quiet and stay hidden. Another major hazard that we were seeing for the nest phase was brown-headed cowbird nest parasitism. So particularly in our early successional sites, we were seeing a lot of failure. So we had 27 nests, or about 23% of our monitored nests, failed due to weather, abandonment, or something else. So a quick summary of some of those numbers I just said. So again, we had 125 nests that we monitored across 14 sites in these 6 years. 67 of those nests were in the young, early successional forest habitats. 58 were in shrubby wetlands. We banded 189 nestlings and had 126 fitted with transmitters. And we spent an estimated total field hours of about 3,444 hours. So you can see probably that this kind of study has some definite limitations. So one of them, as that last slide hopefully demonstrated, is just how high effort they are. It takes a ton of time to go through all of these phases. Nest searching is really, really intensive and difficult. It is, we're just out in the field all day, every day for collecting as much data as we can, but it takes a lot of time. It's also really expensive. So transmitters are expensive, and then obviously labor is very expensive. And then it is also very intrusive. So particularly when we're visiting the nests, it can be pretty intrusive. We really try to limit that because we want to minimize our disturbance, but we do have to visit the nest to get transmitters on. It's just an inevitable part of this kind of work. But we have to kind of find the sweet spot too. So you can see that the nestlings look very sad and tiny and pathetic. So we put transmitters on at that phase when they are at, it's called pin break, so it's when their feathers are starting to emerge from their pins. But these guys only stay in the nest for 9 days. So this is a 7-day nestling. It looks crazy, but within a couple of days, they reach this phase by the time they actually fledge. But we have to find that sweet spot because we need them to be big enough that the harness will fit them, but we don't want them big enough that we'll accidentally force them to fledge. So it's finding a sweet spot, but it is intrusive. But because of all of these, high effort, expensive, we want to make sure that we get as much use out of our data as possible, and so this is where modeling comes in. So the model that I am using is built around the annual cycle. So this represents just kind of broadly the annual cycle of migratory birds. So we have our breeding season down here, which is where we're collecting our data. They're up here. That's their only chance in the year to grow their population, and then they spend the rest of the year just trying to survive so that they can get back and increase their population again. So most study on the annual cycle really focuses on the adult annual cycle, and so our hope with our juvenile field data is to incorporate a juvenile component to an annual cycle model. So the model that I am using is called the endogenous life cycle model. It was developed by Matt Ederson, and it is a Markov chain model. So it is a matrix-based model. So So it's a matrix-based model that is, iterative and multi-stage. So it has rows representing every day of the year, and then the columns represent different kind of phases that an individual can be in. So for like migration, non-breeding, and the other migration, it really just looks like survival or death. But during the breeding season, it's a lot more robust. And we'll talk about that a little more in a second. But one of the really big benefits of this kind of model is because it's because it's matrix-based, there's basically a different cell in the matrix for every different thing that can be happening on any different day, so it's highly adaptable. Okay, so like I said, right now the model has a really, really robust breeding season component, but it's really just looking at nesting. So the output of the breeding season section of the piece of the model is fledglings per female, or it can also just be broods per female. And so within the breeding model season, we have all of these different phases that are considered, and we have basically probabilities that an individual will move from one phase to the next. So this image over here is kind of what the output of the model gives us. So if we look here at day 20, we can see that on day 20 of the breeding season, we would expect an individual or a certain percent of the population, but for an individual, we would expect there's about a 10% chance that they will be red. So that means that they failed due to some environmental cause, some other cause. So that could be predation, that could be, a weather event, any of the things we talked about. About 80% chance that they will be actively incubating a nest. And then there's about a 10% chance that they'll be in this dark blue, which means that they're going through the pair formation copulation phase. And so those are individuals who already had a nest fail, but enough time has passed that they are attempting a renest. Okay. So because we have all this great field data for juveniles, we can combine what the ELM model does right now to refine juvenile survival. So currently, like I said, the breeding season output is a number of young fledged per female. But throughout the rest of the year, their survival is just predicted as 50% of adult survival. So we basically take that number of juveniles that fledged, 50%, and then take 50% of adult survival. That's how many we expect to make it to the next breeding season. But because we have all this great juvenile field data, we can hopefully refine this part of the model and build juveniles in as their own, with their own survival data. So, by parameterizing the model with our field data, we can learn some different things. So we can consider how different juvenile survival rates can affect the overall trend of a population. So how different is the annual population trend with quote-unquote good juvenile survival versus normal survival or bad survival? So for instance, within our golden wing data, we had a year of really high survival in 2023. So we had no weather-related mortality and really limited predation mortality. But then in 2024, we saw extremely high rates of mortality because of numerous things. One thing is that there was a massive storm in June that resulted in a lot of renesting, and people saw that across different species too. Usually renests have fewer eggs, and it's really energetically costly for the adults. And there was also quite a bit of nest parasitism and predation. We can ask the question, hopefully answer the question, how does the population trend differ between those 2 years, between 2024 or 2023 when we had the good juvenile survival? What does that mean for the population as a whole versus this bad survival year? What does that mean for the population as a whole? And this is what I'm doing for my thesis project. It's still in progress, so I don't have actual data for you here, but hopefully I will soon. Okay, so what does this all mean for conservation? So first off, it can help us think about what life stages to prioritize in management and how. Typically, breeding season management is really focused on the nest phase, which is really valuable and really important, also a lot easier to study. But there's evidence, as Kara mentioned, that that fledglings have different needs than breeding pairs do. And so if we are managing for the nesting phase but not considering fledglings, how much effect are we going to be able to have on that population? Also, because we have these really robust habitat surveys that were built into our field data collection, we'll be able to incorporate specific habitat parameters, so like variables to capture like forest structure things like Josh was talking about that are really important for breeding birds. And then by running the model with survival under those different habitat conditions, we're hoping to better be able to prioritize specific habitat variables that might have the greatest effect on the annual population trend. We'll also be able to better understand the effect of these different phases. And we can consider how extreme weather conditions affect a population. So like in that earlier example, we can look at what happens for the population as a whole, even if the rest of the breeding conditions are good. If we have that early season storm, we can kind of work with the model to get it to model what that looks like. But because we have nest habitat data too, in conjunction with that habitat data with the survival data, we can consider whether there are any particular habitat conditions that helped to mitigate the nest failure in that big storm. Because obviously we can't control our weather events, but hopefully there's some other habitat covariate that we can affect. So we can also consider how the annual trend can fit into the broader, longer-term trends. So what would a population look like after 5 years of that quote-unquote good survival? Or what about 5 years of bad? And how many years of that bad survival would it take for a population to shrink to a point of collapse? So these are some of the things I'm thinking about. But also, it's just really important, again, we put so much work and effort and money and time into collecting this data. And so it's really important that we get the most utility out of it that we can. All right, thank you. I can take questions.
Hi, does your habitat data include how far the nests are from a road?
So we do have some distance to edge. The edges at our different sites are a little different, so not all of them are that close to roads at all. But we do have some distance to edge measurements, yeah.
Does your field study have any evidence of increased predation by your having a camera, you're having to go there, you're setting a trail, and your scent is there?
Yeah, 100%. So that's a really good question. So that is something that we're really careful about when we visit nests. We don't spend any time on nests. We try to make the trail not go up to the nest. Unfortunately, it's hard to measure our actual effect because if we're monitoring the nest, there's going to be some level of us going to it. But that's a really good question.
My question is did you encounter any hybridization between the golden winged warbler and the blue winged warbler?
Yeah, another good question. So we did encounter a few hybrids. We had different sites kind of at different places in the state, and we encountered more hybrids some places than others. So like our last year, we didn't have any hybrids, but the year before that, we had a handful. So we definitely did encounter some, but largely we were still seeing just golden wings.
What are some of the reasons why the golden-winged warbler population seems to be moving towards Minnesota?
So we have a lot of appropriate habitat for them. This is, I can't answer this question in great detail because the actual Golden Wing Field project is not so much my project. But if you want details, Alexis Grandy is here and would be happy to talk to you about that.
So my original question was about the hybridization overlap zone and things of that sort, but I'm curious if there's been thoughts between yourself and the other gentleman that was just up about LiDAR and the potential habitat makeup that makes that preferable for blue-winged warbler versus golden wing, and where that's happening and what specifically they're keying in on and why that overlap is occurring.
That's a really good question. That's not something we've spent specific time looking at, but it's definitely something we talk about and think about a lot. But we haven't gotten to any analysis around that.
Hi there, thank you. I moved here from out east last year, and I spent a lot of time in West Virginia up in the mountains with golden wings. I've noticed on your map that golden wings have been almost completely extirpated from West Virginia. But what they're doing there, a few different groups, mostly with West Virginia University, is to manage habitat to try to lure golden wings back, which usually involves just clear cutting to bring the systems back. I haven't seen a single example of that working anywhere. And I was around enough to know that the areas they're trying to do this, and there were never golden wings. Is any of that habitat, I hate to call it management, but is any of that habitat destruction to bring higher golden wing density back happening in Minnesota?
So that's another really good Alexis question. That's a good Alexis question.
Alexis is over here if
Yeah.
you want to ask her questions.
She's the woman in the great bird sweater.
Hello. I had a couple of little questions about the nest predators. What was the primary nest predator? And when looking at the nests that were parasitized by brown-headed cowbirds, what percentage of those failed?
That is a good question. I don't have the numbers on either of those in front of me. I would guess that our most common predator was squirrels, probably. But yeah, I'm not positive about the failure rate of cowbird nests.
I would like you to just add a few sentences on how you maximize the value of this expensive data. Like, how is it expanded? How can it be more useful?
Yeah, so by fitting it into the annual life cycle model, our goal is to contextualize it within the whole life cycle. Because again, right now, so juvenile survival data is so difficult to get, and this is a way it's not typically being used right now. So we're trying to build up this model so that we can incorporate it in, because the juvenile survival is so important for the survival of a population, and it really, being able to study juvenile survival is such a recent thing. We were only able to put transmitters on these guys in the 90s. And so we're really just trying to build this new tool as another way to apply that data.
Thank you, Amanda.